Hello and welcome friends. By this particular module, you are sufficiently clear about the basic concepts of air pollution. You already know what air pollutant is, what are its sources, as well as the associated effects. In this particular module, we wish to discuss about the units of measurement and expression of air pollutants. We'll discuss about the introduction to the pollutant concentration and related gas laws, types of expression of units, determination of volume, temperature, pressure relationship, interrelationship of mass and volume based expressions, and we'll also discuss about some particular cases. So as you learn the content, you will be able to explain the importance of pollutant expression, state applicability of the gas laws for expression of the units, determine the concentration of air pollutant and convert the same from one unit to other. This pollutant concentration is very important aspect of pollutant. Its fate as well as its transport in the environment as well as various engineered systems meant for the establishment of the control on that particular pollutant. Also, certain rate of chemical reactions as well as the toxicity associated with the pollutant is often determined by the concentration of the pollutant. However, these particular pollutants are routinely expressed in variety of the units. Say for example, if certain automobile engineer is interested in expressing the efficiency of the engine he has devised, he may be more concentrating on the efficiency of the fuel. Whereas, if the same engine is experienced by some environmental engineer, he would be more interested in knowing the mass of the pollutant being emitted through the operation. So as many as disciplines associated with the air pollution and even control, one could use variety of the units. However, in order to build up the consensus, one must be able to convert the units from one set to other. Very often, these pollutant concentrations are depending on the medium of the pollutant. Say, if we are dealing with air, we could be interested in mass per unit volume, volume per unit volume. If we are dealing with certain water, it could be mg per liter. If we are dealing with certain soil, it could be mass per mass and accordingly. So, this expression of the pollutant will depend on the purpose of the measurement. It is also quite probable that whatever the kind of the equipment that we are using for the measurement, accordingly the unit may also change. However, in air pollution, as we are more interested in the atmosphere as a whole, which is associated with the mixture of the gases as we discussed earlier, these gases are important not because only the pollutant may exist in the gaseous form. However, these gases also provide certain medium in order to have the transport of that particular pollutant, according to which the fate of that particular pollutant is decided subsequently. Also, for most of this particular air pollution work, expressing the pollutant concentrations in compatible terms is very customary. As an environmental engineer, as we deal with the calculations for the gas concentrations, we have to assume certain gas laws. These gas laws already we have studied in the physics in our early standards, but to have the revision would definitely important. So according to the Boyle's law, the value of the gas under constant temperature is inversely proportional to the pressure, which is expressed as V proportional to 1 by P. The volume of the gas under constant pressure is directly proportional to the temperature expressed in the Kelvin scale according to the Charles law, and it can be expressed as V proportional to T. Also, V1 by T1 has to be equal to V2 by T2. The pressure of the gas of a constant value is directly proportional to the temperature expressed in the Kelvin scale according to Gay-Lussac's law, which is expressed as P proportional to T. Also, P1 by T1 is equal to P2 by T2. Thus, when measuring the contaminant concentration, we must know at what atmospheric temperature as well as the pressure the measurements are made. Also, the presumption is at standard temperature and the pressure, 1 gram mole of ideal gas occupies 22.4 liters. So this standard temperature and pressure is considered as 0 degrees centigrade and 760 millimeter of H. So we can summarize that the units could be expressed in various types as mass of pollutant by total mass, say for example milligram of kg. It can also be expressed as parts per million as mass, or mass of the pollutant by total value such as mg per liter or milligram per cubic meter. Also, volume of the pollutant per total value, say ppm based on value. Also, moles of the pollutant per total value, as such moles per cubic meter. So we will more concentrate on the gaseous pollutants. So units of volume of fraction or mole fraction are frequently used in order to express gas concentrations. The most common volume fraction units are ppm V, that is ppm by value. These volume to volume units have certain advantage that the concentration remains unchanged as gases are compressed or expanded. It is easy to note that if these concentrations are expressed on mass volume basis, it will be changing according to the expansion in the gas. Say, it is obvious that this concentration will be decreased as the gas expands. To convert the gas concentration between the mass per value and value per value, we can resort to ideal gas law, which is expressed as PV is equal to nRT, where this P is a pressure, volume taken up is equal to number of moles into R, which is ideal gas constant, multiplied by the temperature in Kelvin. This universal gas constant could be expressed in many different sets. Say for example 0.82056 liter atmosphere per mole Kelvin, 8.205 into 10 raised to minus 5 meter cube atmosphere per mole Kelvin, and even some other expressions. So depending on the kind of the computations that you are doing, you can make use of the value of R. The units based on the volume mixing ratio, usually parts per million or part per billion, or also these parts per trillion. One must not confuse the abbreviation PPT associated with parts per thousands. This unit expresses the concentration of the pollutant as ratio. Its value, if isolated in its pure form, to the value of the air mixture in which that particular pollutant is present. While expressing this value mixing ratio, we assume the ideal gas behavior. Thus, the concentration won't be depending on the temperature as well as pressure, because the phenomena will be affecting both the pollutant as well as the mixture of the air equally. As a consequence of this particular ideal gas law, a gas present at a volume mixing ratio of 1 ppm could be 1 centimeter cube per 10 raised to 6 centimeter cube of polluted air, 1 mole of the pollutant per 10 raised to 6 mole of the air, 1 molecule per 10 raised to 6 molecules, and it has a partial pressure of 1 millionth of the atmospheric pressure. Let's revise the concept of determining volume, temperature, and pressure relationship. From our earlier discussion, it is clear that the liters per mole is influenced both by temperature as well as the pressure. As we consider the Avogadro's law, 1 mole of any gas occupies the same volume of as 1 mole of any other gas at same temperature and pressure. So to convert this liter per mole at other conditions, we can make use of the expression P1 V1 by T1 is equal to P2 V2 by T2, where the P1 V1 T1 are associated with the standard conditions, whereas P2 V2 T2 could be the actual conditions. So here the small problem can make this concept very clear. If the volume occupied with the 2 mole of the gas at 25 degrees centigrade and 820 mg, what can be the volume occupied at other conditions? So accordingly here, as we refer to P1 V1 T1 as standard conditions here. So accordingly, the volume occupied at the actual conditions can be determined as 45.32 liters. Another example which is helping us to determine the concentration in gas. So 100 liter of the gas mixture has 10 raised to minus 7 moles of carbon monoxide. We want to determine the concentration in microgram per cubic meter. So the given concentration is 10 raised to minus 7 mole of carbon monoxide per 100 liter. So here we can consider the 20 gram of carbon monoxide per mole of CO. As we convert these particular grams into micrograms, and as we convert the cubic meters into the liters into cubic meters, we can work out the solution as 28 microgram per cubic meter. Sometimes there could be requirement to determine the gas concentration in volume or mole fraction. So a gas mixture contains 0.001 mole of oxides of nitrogen and 0.999 moles of air, express NOx concentration in ppm based on value. So this concentration of oxides of the nitrogen will be VNOx divided by V total into 10 raised to 6. This volume of oxides of the nitrogen can be used by making use of ideal gas law, and accordingly it can be determined as 0.001 mole of oxides of nitrogen into R into T by P. Based on the similar calculations, the total volume can be worked out as 0.001 plus 0.999 moles total into R into T by P. So, as we determine this ratio, the answer is 1000 ppm based on value. Here, we wish to derive the relationship or rather interrelationship between the mass based and value based expressions. So for air pollution studies, it is customary to express the pollutant concentration as volumetric units. However, most of the times we prefer to have that particular concentrations expressed as microgram per cubic meter or milligram per cubic meter. So this expression can be deduced by making use of ideal gas law. PV is equal to nRT. Already we are acquainted with this. Also, we know that 1 mole of any gas has Avogadro's number of the molecules, 6.02 into 10 raised to 23 molecules per mole. We know the terms R as well as T. So in order to determine the volume of ideal gas by making use of this relationship PV is equal to nRT at standard temperature and pressure. So this volume will be equal to nRT by P. N here is 1 mole. R, the value we already have. This standard temperature on Kelvin scale is 273, whereas the pressure is 1 atmosphere. So accordingly, this value comes to be 22.41 liters. Whereas, if we try to determine the same value at different temperature, that is 25 degrees centigrade, it comes to be 24.465 liters. As such, we can determine the volumes getting varied with the temperature by carrying out similar calculations. Thus, at standard temperature and pressure, this milligram per cubic meter can be expressed as ppm into 1 cubic meter pollutant by 10 raised to 6 meter cube of air per ppm. As we consider the molecular weight and the conversion of grams into milligrams, here we reduce this expression to ppm into molecular weight divided by 22.414. Similarly, at 25 degrees centigrade, this expression would alter its form as ppm into molecular weight divided by 24.465. So in general, this expression can be put up as milligram per cubic meter is equal to ppm into molecular weight divided by 22.414 into 273.15 Kelvin divided by temperature in kelvins into pressure, atmospheric pressure divided by 1 atmosphere. Say, we wish to convert these parts per billion into microgram per cubic meter. According to the given data, the gas mixture has SO2 concentration as 100 ppb based on value. We wish to determine the concentration in mass per volume basis for given temperature of 25 degrees centigrade and atmospheric pressure of 1. So this 100 ppb would be nothing but 100 cubic meter of sulfur dioxide divided by 10 raised to 9 cubic meter of air. So in order to convert this volume of SO2 in units of mass, let's first determine the equivalent number of moles by making use of expression. Here, as we solve for this particular expression, we get it as 4.09 into 10 raised to minus 6 moles of SO2 per cubic meter of air. So these moles can be converted to mass using the molecular weight. So as we multiply the answer that we got in this particular step by multiplying it 64.1 gram per mole into 10 raised to microgram per gram, answer comes to be 260 microgram per cubic meter of sulfur dioxide. Also, the ppm units can be converted into milligram per cubic meter. So based on the given data, here the Federal Air Quality Standard for carbon monoxide based on 8-hourly measurement is 9 ppm. Express the standard as percentage by value as well as in milligram per cubic meter at 1 atmosphere and 25 degrees centigrade. So within million volumes of the air, there are 9 volumes of carbon monoxide irrespective of temperature and pressure. Hence, percentage CO will be 9 into 10 raised to minus 6 into 100, which comes to be 0.0009. Also, already we have devised this particular expression. Milligram per cubic meter is given as ppm into molecular weight expressed as gram per mole divided by 24.465 at 25 degrees centigrade and 1 atmosphere. Hence, as we substitute this particular value and as we take into account the molecular weight of carbon monoxide as 28, the answer comes to be 10.3 milligram per cubic meter. The units that we discussed so far are very conventional and practically adopted by all the environmental engineers in the air pollution studies. So, microgram per cubic meter or ppm are interconvertible. As we are dealing with the particulate matter, we usually go for microgram per cubic meter. Additionally, we may be dealing with a particular case of, say, fallout of particulate. So, in order to express that, we can make use of the units milligram per centimeter square per month or milligram per centimeter square per year. Also, there could be need to determine the particulate count. It could be expressed as number per cubic meter, such as million, that is 10 to 6 per cubic meter. Now, as we are in the learning phase and as we learn different phenomena associated with the air pollution, say for example, if we are using certain satellite data, if we are trying to correlate the deaths associated with the air pollutant concentrations, so at that time there may be requirement to understand the annual exposure of certain pollutant. Say for example, mean annual exposure to PM 2.5 pollution. Also, certain guidelines are given by WHO in order to determine the percentage of the total population exposed to PM 2.5 given by certain guide values. Also, these oxides of the nitrogen consists partly of NO as well as NO2. So the volume fraction in air ppb equates to a different air concentration in microgram per cubic meter depending on the ratio of NO to NO2. Hence, the concentration of the oxides of the nitrogen are normally expressed as microgram oxides of the nitrogen based on nitrogen dioxide per cubic meter. So, all references assume that oxides of the nitrogen is in the form of nitrogen dioxide. Some pollutants like sulfate, nitrate are present as particles in the air, and the concept of volume mixing ratio of the gas is not applicable. Hence, their concentrations are required to be expressed in the form of microgram per cubic meter. Also, as we know that the volumetric content is depending on the temperature as well as the pressure for a given reason. Hence, to maintain the uniformity for the expression, the volumetric contents are expressed as normal cubic meter. So that normal cubic meter is expressed as n cubic meter, meaning the measurement at standard temperature and pressure as we discussed previously. So thanks for your attention. I hope the discussion that we made in order to understand the measurement of air pollutants and their expression will be useful for your study. So thanks for your attention. As we move ahead, we will discuss about the air quality standards laid down by various countries. So bye till then. I wish you very happy learning. Thank you.